This is the demo for lesson 9 in college algebra. First, we're going to talk about radical equations. So those are equations that have a radical sign in them or a root sign. And the key to solving is to isolate the radical and then raise both sides to an appropriate power. So you want to get the radical by itself as the first step. So in this example, I'm going to start by subtracting x from both sides. So I have radical x equals 12 minus x. And then I want to get rid of the radical, to get rid of a square root, you can square both sides. So my next step is going to be square both sides. And when you square a square root, they cancel, and we just have x on the left. And 12 minus x squared, that means 12 minus x times 12 minus x, and we have to FOIL that out. Very common mistake people make here is to write 12 squared minus x squared. But we have to do the whole multiplication out. So when I FOIL this, 12 times 12 is 144. That's first. Outer, minus 12x. Inner, minus 12x. Last, plus x squared. So we have x equals 144 minus 24x plus x squared. And then I need one side to be 0 in order to solve a quadratic. So I'm going to subtract x from both sides. And I get 0 equals x squared minus 25x plus 144. So usually the quickest way to solve a quadratic is by factoring if it's factorable. So we're just going to quickly ask ourselves, are there two numbers that multiply to 144 but add to negative 25? So 12 and 12 multiply to 144, but they don't add to 25. So I need to test some other numbers. 144 is going to be divisible by 9 because its digits add up to a multiple of 9. So 4 and 4 is 8 and 1 is 9. That's a little divisibility trick. If you didn't know that, you could just test numbers on your calculator. Do 144. It's definitely not going to have 5 go into it, but like maybe 4. Yeah, 4 and 36, but those don't add to 25. And then we could try 9. And 9 goes into 144 16 times, and 9 and 16 do add to 25. So that is how I'm going to factor it. So it's going to be x minus 9 times x minus 25. And then we set each factor equal to 0, and we get x minus 9 equals 0, or x minus 25 equals 0, and we get x equals 9, or x equals 25. And then, especially with radical equations, you really need to check the solution because sometimes you get what's called an extraneous solution. So let's see, I'm going to have 9 plus root 9. Does that equal 12? So that's 9 plus 3 equals 12. That is true. So 9 is a solution. And then if I plug 25 in, I'm going to have 25 plus the square root of 25. Does that equal 12? 25 plus 5 is not 12. It's 30. Okay, so 25 is not actually a solution. We call this extraneous. It sometimes happens when you square both sides of an equation. Okay, the next type of equation that we're going to study are equations with rational exponents or fractional exponents. And the key to these is to isolate the term with the rational exponent, and then we'll have two methods. We can either convert to a radical equation, which we just practiced solving in the last example, or we can solve by raising both sides to an appropriate power. So let's start by isolating the radical. I'm going to add 8 to both sides to get the x term by itself. So I have x to the 2/3 equals 4. And then I'm going to do the converting to a radical method. So that's a cube root. So I'm going to say the cube root of x squared equals 4. And you can put this squared outside the radical or inside the radical. It's the same. And I'm actually going to put it inside because I don't want a square root yet. I'm going to put it there. And then my next step to undo the cube root would be to cube. So I'm going to cube both sides. And what I'm left with is x squared equals 4 cubed is 64. And then I square root both sides and I get x equals plus or minus 8. Okay, and then my other option would be to, once I have the x term isolated, I can raise both sides to a power so that what I end up with is x to the first. So x to the 2/3 equals 4. And I'm going to raise both sides to a power, strategically chosen. So I want to put a power here and a power here, raise both sides to the same power, and I'm going to choose that power to try to make sure that on the left I end up with x to the first. Okay, and when you raise a power to a power, like in the preview exercises, you multiply the exponents. So 2/3 times what would give me 1, 3/2. So I'm going to raise both sides to the 3/2 power. So x is 4 to the 3/2. And we get the square root of 4 cubed. And when I take the square root, I actually need to put the plus or minus in there because technically I'm taking a square root. When I raise both sides to the 3/2, that 2 is in the bottom. It's a square root. I'm taking the square root of both sides. So I need to put in the plus or minus. It's trickier to remember the plus or minus when you do this method. So I tend to stick to this method so that I don't forget. So plus or minus 4 to the 3/2 would be the square root of 4 cubed. So the square root of 4 is 2, and 2 cubed is 8. Moving to linear inequalities. The key to solving a linear inequality is to treat it just like a linear equation. So even though this sign is a less than, we could treat it as though it's an equal sign, but with one small difference. Whenever you multiply or divide both sides by a negative number, multiply or divide by a negative, you have to reverse the direction of the inequality. So for example, negative 4x is less than 8. To isolate the x, I would divide both sides by negative 4. And on the left I have an x, and on the right I have negative 2. But because I divided by a negative, right, if you multiply or divide by a negative number, you turn the inequality around, reverse it. So this is going to become x is greater than negative 2. And then to express our answer using set builder notation, graphed on a number line, and interval notation, well, this is almost set builder. I just need to add some curly brackets. I would say, well, this is the set of all x's such that x is bigger than negative 2. If I put that on a number line, here's 0, here's negative 2, and I want all numbers bigger than that, so I'm going to put a round bracket, because I'm not including the negative 2, and then all numbers to the right are the bigger numbers. And then interval notation would be smallest number, negative 2, to the biggest number, infinity. We're not including the endpoint, and we never include the infinity. Compound linear inequalities. The key to solving these is to treat it like an equation that has 3 sides. Whatever you do to one of the 3 pieces, you must do to all 3 pieces, and the goal is to isolate the x in the middle. You also have to follow that rule about turning the direction of the inequality around if you multiply or divide by a negative sign. So if I want to get this x alone in the middle, I just need to add 4, because the negative 4 plus the 4 will cancel and I'll have just an x, but I have to add it to all 3 sides of this equation, or inequality. Negative 6 plus 4 is negative 2. X minus 4 plus 4 is just x, and 1 plus 4 is 5. So negative 2 is less than x is less than or equal to 5. And then we want to put this in set builder, number line, and interval notation. So this is almost in set builder notation. This is a piece of that. So we'll do that first. We have the set of all x's such that -2 is less than x is less than or equal to 5. And then for a number line, we've got 0, -2, and it's all the numbers between -2 and 5, and we're going to not include the -2, so I put a round bracket, and the 5 is included because it's or equal to here, so I put a square bracket at the 5, and then we highlight all the numbers in between. And then I can mimic this to do interval notation. I go -2 to 5.